Two USB-C cables sit side by side on a desk. Same reversible connector tip, same metal shell, same black plastic tongue clicking into the same port on the bottom edge of a phone. One cable plugged into a wall charger brick with 65 watts printed on its faceplate charges the phone at full speed. The other, plugged into an identical looking charger, delivers a trickle, slow enough to drain the battery while the screen stays on. Everything looks the same. The outcome is different. That gap between the shape of the connector and the behavior behind it is the central problem of USB-C. A reversible plug arrived in the mid-2010s and promised to replace the tangle of proprietary power bricks, barrel jacks, micro USB cables, and lightning ports that filled junk drawers worldwide. One connector for phones, tablets, laptops, monitors, docks, and power banks. A wall charger box with a wattage badge, a braided cable with a molded strain relief, a laptop spec sheet listing USB-C beside a port diagram, all implied convergence. Fewer cables in the bag, one charger for every device, a single cable from a dock to a laptop replacing a nest of adapters. The visible plug was universal. The hidden contract was not. The promise was real. The conditions attached to it were invisible. At the point of purchase, USB-C is the connector shape. Most of what users care about behind it, charging speed, data throughput, video output, depends on additional capabilities and specifications the connector itself does not reveal. Each is optional. The connector reveals none of them. Power delivery works as a conversation. A phone plugged into a charger sends a request. It states which voltage and current combinations it can accept. The charger responds with its own list of supported profiles. For example, 5 volts at 3 amps, 9 volts at 3 amps, and 20 volts at 3.25 amps. The two devices settle on the highest mutually supported profile and power flows at that rate. The cable between them, however, carries its own constraint. A thin, passive USB-C cable rated for lower current may silently limit what the charger can deliver. An electronically marked cable called E-marked carries a chip that reports its current and voltage capacity to both ends. Without that identification, higher current charging modes are unavailable, and the connection falls back to a lower profile. The braided cable on the shelf may or may not contain that chip. The receipt reads USB-C cable either way. Each layer adds a dependency. The charger's wattage printed on its faceplate means nothing if the device cannot request that profile. The device's maximum charging speed means nothing if the cable gates the current. A multi-port charger may reduce its output across shared ports when a second device plugs in, dropping from 65 watts to 45. No notification, no indicator on the charger's housing. The power just divided itself and told nobody. None of this is marked on the cable tie or the box's small icons row. Data capability adds another invisible axis. A USB-C port on a laptop side might support USB 3.2 speeds, or it might support only USB 2.0, the older, slower protocol running through the same physical opening. A braided cable with a right angle connector might carry data at 10 gigabits per second, or crawl at 480 megabits per second. Naming made this worse. USB 3.0 launched under one name. It was later renamed USB 3.1 Generation 1, then renamed again to USB 3.2 Generation 1. The speed never changed. The label changed 3 times. A buyer comparing two cables with different generation labels on the packaging might reasonably assume one is faster. Some USB-C ports carry video. Some do not. The connector is identical either way. A USB-C hub with an HDMI port, an SD card slot, and an Ethernet jack relies on the host device to provide both power and optional display capability over the same connector, a feature sometimes called alternate mode. Plug that same hub into a different laptop and the HDMI output may go dark. The monitor shows no signal. The hub's status LED blinks. Nothing in the hub's packaging warned of the dependency. Lived experience turns these layered dependencies into a cable lottery. A laptop dock with a cable lock slot and a bundled power adapter functions perfectly on one machine. The same dock, connected to a different manufacturer's laptop through the same cable, delivers data to the Ethernet jack but fails to push video to the monitor. A power bank with USB-C input and output labels and a small display showing charge level negotiates full speed charging with one phone and drops to a trickle with another, identical port shape, different profile support. A troubleshooting sheet packed with a docking station lists failures by symptom, charges slowly, device not recognized, and display not detected. Each heading maps to a different broken negotiation between the device, the cable, the charger, or the dock. The root cause is optionality. The USB-C specification defines the connector, power delivery defines charging negotiation, alternate modes define video output, data speed tiers define throughput. A device manufacturer can implement any combination, for example, full power delivery support but no alternate mode, USB 2.0 data but fast charging, or video output capped at a lower resolution. A cable manufacturer can build a cable that passes power and data but lacks the wiring for video. A power delivery logo on a charger retail box confirms power delivery support at some wattage, but the row of small icons beside it may not disclose which voltage profiles are available. A charger says 65 watts. A phone says 65 watts. The cable connects them, and the phone charges at a crawl. The numbers matched. The protocols did not. Several device manufacturers built their own charging schemes outside power delivery, using the same USB-C connector but different signaling. A charger designed for one proprietary scheme may fall back to a much slower baseline charge on a device expecting standard power delivery negotiation. A fast charge badge on a cable's packaging or a GAN sticker on a compact wall brick tells a buyer something about the hardware's capability, but nothing about protocol compatibility with the device in their pocket. Regulators noticed. In the European Union, common charger rules mandated USB-C on covered devices and tied harmonized wired fast charging in covered product classes to USB-C power delivery. Phones and many small electronics are covered from the end of 2024, with laptops following in 2026. The USB Implementers Forum tightened its certification and logo guidance. It paired wattage and speed on certified cable markings in more legible formats. The Trident style mark from the USB Implementers Forum on packaging began to mean something testable. Proprietary fast charging schemes increasingly adopted USB power delivery as a base layer rather than replacing it entirely. The ecosystem is moving toward treating a USB-C port as a declared set of tested capabilities rather than a socket with hidden limits. The shift is real, it is also still incomplete. Two cables still sit on the desk. Same plug, same shell, same shape. One works, one does not. A universal connector becomes a universal standard only when the capability behind the port is legible at the point of purchase and consistent at the point of use. Shape alone is a housing. Certification, clear labeling, and fewer optional states turn a housing into a contract.